Making decisions and finding insights from raw data is an essential part of data science. And one such algorithm which is widely used for this purpose is decision tree. Hence, keeping the importance of decision tree in mind, we have come up with this comprehensive course. Now, before we go ahead with the session, I'd like to inform you guys that we've launched a completely free platform called Great Learning Academy, where you have access to free courses such as AI, cloud, and digital marketing. You can check out the details in the description below. Now, let's have a quick glance at the agenda. So we'll start off by understanding what exactly is machine learning and what is the decision tree algorithm in machine learning. Then we'll go ahead and implement the decision tree algorithm with the R programming language. After that, we'll understand the concepts of entropy and Gini index. Going ahead, we'll understand what exactly is overfitting and how can we prevent overfitting in decision tree. And finally, we'll understand Shannon's entropy. So let's start off with the session.
All right. So we'll understand machine learning with this little example over here. So what do you see in this slide? What is this exactly? Well, it's a fish, isn't it? And what is this? Well, this again is a fish. And how about this? Well, this too is a fish. Now, how do you know all of these are fish? Well, as a kid, you might have come across a picture of a fish and you would have been told by your kindergarten teacher or your parents that this is a fish. And your brain learned that anything which looks like that is a fish, right? And that is how our brain functions. But what about a machine? Now, if I take this image of a fish and I feed it to a machine, will it be able to understand that this is actually a fish? Well, this is where machine learning comes in. So what I'll do is I'll take all of these images of the fish and I'll keep on feeding them to this machine until it learns all the features associated with this fish. Now, when I say all the features associated with this fish, so the features would be, let's say a fish has two eyes, it has two fins, it has a tail, it has gills, and so on. So this machine would learn all of these features associated with the fish. Now, once the training is done, it is given new data to determine how much it has learned. So what I'm basically trying to tell you is, first the machine is given training data. So first the training is done. And once it learns all of the features associated with the training data, it is given the test data. So this is where we are actually testing the machine how much it has learned. So we have given this new image of this fish to this machine and we are trying to estimate whether this machine is able to correctly label this image as fish or not. So this is the underlying concept of machine learning. Right, and now that we know what exactly is machine learning, we'll have a look at the categories of machine learning. So machine learning can be broadly categorized into supervised learning and unsupervised learning. And we'll start with the first one, which is supervised learning. So in supervised learning, you basically have output variables and input variables. And these output variables are denoted with Y and the input variable is denoted with X. So these output variables are also denoted as dependent variable and this input variable is also known as an independent variable. And we are trying to determine how does an output variable change with respect to an input variable, or basically how does a dependent variable vary with respect to an independent variable. So this what you see, Y equals fx. So over here Y would be the dependent variable and X would be the independent variable, and we are trying to determine does Y vary with X or not. So again, supervised learning can be broadly categorized into regression and classification. So we'll start off with the first one, which is classification. So as you see over here, classification is basically the process of predicting the class of a new variable. Now let's take this example to understand classification better. So let's say we want to determine whether a person has cancer or not on the basis of whether the person smokes or not. So over here, whether the person has cancer or not would be the dependent variable, and whether the person smokes or not would be the independent variable. So we basically have a data set which would comprise of two columns, and one column would be the person, whether he has cancer or not, and then the next column would be whether the person smokes or not, right? And on the basis of this column, we are trying to determine whether the person has cancer or not. And this is basically the underlying method of classification. Now there is another method known as regression. So as it is stated over here, this method is basically used to find the linear relationship among different entities. So over here we have a dependent variable and we have the independent variable. So the dependent variable is denoted with y and the independent variable is denoted with x. Now, what happens in regression is, let's say if I put in some random value of x, we would have to get a value of y for that. So this is what is basically known as regression. So for an arbitrary value of x, we are trying to find out a corresponding value of y. Now, we'll head on to the most important part of a session, which is decision tree algorithm. So decision tree algorithm is a supervised learning method which is used for both classification as well as regression purpose, right? So you can both classify the data. Also, you can use it to find out what is the relationship between y and x. So let's understand the decision tree algorithm with this image over here. Now let's say I have this very simple question. So I want to know whether so my question is this: I want to know whether I can watch the movie Avengers or not. And for this, I have a set of decisions to make. So what you have is basically a tree-like structure, and this tree-like structure is decision tree over here. So we'll start off with the first condition over here, which is whether I like Marvel movies or not. And if I like Marvel movies, I'll come onto the left side of it, right? So it is yes. And then again, I'll check the second condition, which is if I am a fan of Robert Downey Jr. Now, if I am a fan of Robert Downey Jr., I will definitely watch Avengers. But if I don't like Robert Downey Jr., then I will not watch Avengers. Similarly, if I don't like Marvel movies, then the next condition would be whether I'm a DC fanboy or not. And if I am a DC fanboy, then I will definitely not watch Avengers because I'm anti-Marvel. So that is why I'll not go and watch Avengers. But on the other hand, if I'm not a DC fanboy, but I really like Scarlett Johansson, then I will go and watch Avengers. But if I don't like Marvel movies and I'm not a DC fanboy and I also don't like Scarlett Johansson, then I'll not watch Avengers. So this is what happens in decision tree algorithm. So we have a set of decisions which we are making over here, and on the basis of the set of decisions, we will go ahead and classify the data. So this is how the decision tree algorithm works. All right. So this is the basic idea behind decision tree algorithm. Now we'll have a comprehensive demo of this decision tree algorithm in both R and Python. So we'll start off with R. So we'll be working with this car seats dataset, and this car seats dataset is actually part of the ISLR package. So I'll go ahead and load this ISLR package first. So to load the package, I will type in library and then given the name of the package, which is ISLR. So I have loaded the package. Now this ISLR package basically has some datasets with it. So I'll have a glance at the different datasets which are part of this ISLR package. So as you see over here, these are all the different datasets. You got the auto dataset, caravan, car seats, college, credit, default, and so on. Out of all of these datasets, I want to work with this car seats dataset, which is basically about the sales of child car seats. Now I have to load this dataset. So this car seats dataset, as you see over here, this is actually capital C. Now I will go ahead and store this in a new object, and I will name that object in car seats over here. So this car seats, what you see, so this is small c and this is capital C. So I am loading this car seats dataset, which is part of the ISLR package, and I'm storing it into a new object and naming that object to be car seats. Now let me have a glance at this dataset first. So I'll just type in car seats over here, right? So this is my dataset. Now I'll have a glance at this dataset properly. Car seats. So we have the description of this dataset over here. So as you see, this is a simulated dataset containing sales of child car seats at 400 different stores. So we have 400 observations in total, or 400 records in total, and there are 11 variables or 11 columns in total. Now these are the different columns. So we've got the sales column over here. The sales column is basically the unit sales in thousands at each location. So this 9.5 would be 9.5 into 1000. So that would be around 9,000 sales. Then we've got comp price column, which is the price charged by competitor at each location. And then we've got the income column over here. So income column would basically tell you the community income level in thousands of dollars. Then we've got the advertising column, which denotes the local advertising budget for company at each location. Then we've got the population column over here. So this would tell you the population size in thousands. Then we've got the price. So price the company charges for car seats at each site. Then we've got the shelf location. So this basically tells you that there are three levels for the shelf location. Either it is good, bad, or medium. And this indicates the quality of the shelving location for the car seats at each site. And then you've got all of these different columns over here. So you've got the age column, education column, urban column, and US column. So you can just go through the description of this entire data set over here. So now that we have looked at the data set, we will start off by our data manipulation purpose over here. So now what you see is we have the sales column. So I want to add a new column which is dependent on the sales column. So let's say wherever the sales is greater than 8. So this 8 actually means 8,000. So wherever the sales is greater than 8,000, I want to denote it with high. And wherever the sales is actually less than 8, I want to denote it as low. And that is what I'm doing with this particular command over here. So I will use this if else clause, and over here I am checking if the sales, the number of sales is actually greater than or equal to 8. And if the number of sales are equal to or greater than 8, then I want it to be denoted with yes. On the other hand, if the number of sales are actually less than 8, then I want it to be denoted with a no. And I'm storing this in a new object and naming that object to be high. Now let me just show you the head of high over here. So I will type in high dot head. So let me go ahead and actually run this again over here. So let me check the class of this, class of high. Right, so this is actually a character. So I'll just put in high over here and I'll get maybe the first 5 elements. So what do you see? You have yes, 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 no, and no. Now let me compare this with this particular column over here. So as you see, the number of sales, it is 9.5, and since 9.5 is actually greater than 8, you have a yes value over here. Similarly, you have 11.2 over here, and since 11.2 is greater than 8, you have yes. Then you have 10.06, which is greater than 8. Again, you have a yes. After that, we have 7.4 and 4.15, which are less than 8. And that is why we have a no value over here, right? So we have basically created a new object where we are getting yes and no values on the basis of this sales column. So now that this is done, what we'll do is we will add a new object. So we will basically add this into this entire data frame, right? So I am using the data frame function over here. Using this, I will basically add this particular object into the car seats data frame, right? So I am attaching this new object as a new column into this data set, and I am storing it back to the car seats data frame over here. Now let me have a glance at car seats, a view of car seats. Now, if you have a glance at this data set, you see that we have added this new column, right? So let me show you the original data set view of, let me put in capital C over here. So this was the original data set which did not have the high column. And if you look at this particular data set over here, we have this high column over here. So all of these yes values denote those cases where the sales is greater than 8. And all of these no values denote where the sales value is actually less than 8. So we have done this, we have added a new column to this. Now this would be our dependent variable, right? So our problem statement for this particular data set would be, we want to understand whether the sales are high or not on the basis of all of these different factors. So I have created this column. Now since this column is actually based on the sales column, I will go ahead and remove this column. So let me copy this and let me paste it out over here. So as you see, what I'm basically doing is I am selecting all of the rows from this car seats data set, and I am also selecting all of the columns except the first column. That is why I put in -1 over here. So when I put in -1, I'll be getting all of the columns except the first column, and I am storing the result back to the same data set over here. So this is done. Now let me have a glance at this data set, view of car seats. So as you see, I have removed the first column, right? So the first column was the sales column, which I have successfully removed from over here. Now it's finally time to build our decision tree model. So we'll go ahead and build our decision tree. So to build the decision tree, we would require this tree package. So first you'd have to install the package. You'll click on packages, you'll click on install, and you will just type in tree over here. And when you click on install, the package would be installed. And since I have already installed it, I don't need to do that again. So I'll type in library and go ahead and load this package. So as you see, I have successfully loaded this tree library. So now that this is done, it's time to build my model. And as I have told you, the problem statement is this. I want to understand whether the sales are high or not on the basis of the rest of the columns, right? So I want to understand whether the sales are high or not on the basis of the income or on the basis of advertising or population or price and so on. So I will go ahead and build this model. So this tree package gives us this tree function, and inside this we are giving in two parameters. So the first parameter is basically the formula where we given the dependent variable and all of the independent variables. So over here our dependent variable is this high column over here, right? So and the independent variable, so I have put in this dot symbol over here. So this dot symbol basically means that I am selecting all other variables as the independent variables except this particular variable over here. So let's take this tilde symbol. So whatever is given on the left side of the tilde symbol, all of those values are so that variable is taken as a dependent variable, and whatever values are given on the right side of the tilde symbol, all of them would be taken as your independent variables. So over here high would be a dependent variable and the rest of the columns would be our independent variables. And I want to build this model on top of the car seats data set, right? So this is the second parameter, and I am storing this in a new object, and I am naming that object to be tree model. So I have successfully built this model. Now let me have a glance at the summary of this model. So I'll use the summary function and I will pass in this object which I have just built. So summary of tree model, and this is what we have. So as you see, so this basically gives us the formula which we had just given, and there are 27 terminal nodes. Now there were multiple conditions, and after those multiple conditions we basically reached to this stage where we had 27 results or 27 conclusions. And then we've got the misclassification error rate and the residual mean deviance. Now you have to keep in mind that the misclassification error rate and the residual mean deviance have to be as low as possible, right? So we have successfully created this model. Now let me go ahead and also make a plot of this. So I will type in plot and I will pass in the same object over here, which is tree model, inside the plot function. So as you see, this is what we get. Now let me zoom this and let me count the number of terminal nodes. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27, right? So as it was stated in the summary, we have 27 terminal nodes over here. Now I will go ahead and add the text to this. So I will use the text function and I will pass in the tree model object inside this, and I have successfully added the text to this plot as well. So the first split is based on the shelf location column. So if the shelf location is bad or medium, then we'll come to the left side of this node or the root node, and if the shelf location is actually good, then we'll come to the right side of this. So as you see, this is the first root node. Now if the shelf location is actually bad or medium, we'll come to the left side. And here we are checking if the price is less than 92.5, and if the price is less than 92.5, we'll come over here and then we'll check if the income is less than 57. Then again we'll check the competitor price, right? So over here this is not clear, so the competitor price has to be less than something, and then we'll come down and we'll get this. Again, over here on the right side, we are checking if the population is less than 207.5. So whether the population is less than 207.5 or greater than 207.5, you basically get a yes. So this yes means that the sales are actually high. So in the terminal nodes, wherever you have yes values, all of those yes values indicate that the sales are high. And wherever you have no values, this indicates that the sales are not high. Similarly, if I come down to this part, so if the shell location is actually good, then my condition is whether the price is less than 135. And then again, I come down over here and I am checking if the price is. So here I'm checking whether it is based in US or not. So if it is not based in US, I'll come down to the left side. Again, I'll check if the price is less than 109. So the price is less than 109 over here, then yes, the sales will be high. Similarly, I'll come down if the price is less than 135, and if the income is also less than if the income is less than 46, then obviously since the income is less, the sales will not be high over there when people are not going to purchase a lot of car seats over there, right? And then on the other hand, if the income is actually greater than 46, then the number of sales would be high over here, right? So this is what the yes basically denotes. Right. So we have built this model, and we have also visualized this particular model over here. Now so this is we have done this without dividing our data set into the testing set and the training set. Now what happens when we don't divide the data into testing and the training set is we actually go ahead and overfit our model onto this data. Now to understand this, I'll give you an example. So let's say you have an exam tomorrow, and you have not studied anything at all, but then again your friend comes to your rescue. He tells you that he has found the he has basically bought the same question paper somewhere, or basically the question paper was leaked, and he tells you that there would be only 5 questions in tomorrow's exam, and he gives you the question paper, and you go ahead and basically learn or remember all of the answers for those questions. Now there are two scenarios. If in tomorrow's exam the same set of questions come in, then you are going to ace the exam, right? You are going to get 5 out of 5. But on the other hand, if none of those questions come in, right? So maybe you are fooled by your friend, or maybe your friend just took money from you, right? And it could also be the case that none of the questions come in. So you have only learned those 5 questions, but in the exam there were totally new questions, and this is the case where you will totally fail. So that is why this is what I'm trying to tell you. You have to divide your data set into training and testing sets. So first you go ahead and train the model, and once your machine knows properly about your data set, that is when you will go ahead and test its capacity. So it's extremely important for you to divide your data set into training and testing sets, and that is what we are going to do over here. So to divide the data set into training and testing sets, I am going to I'll be needing the CA tools package. So I will go ahead and load this library, which is CA tools. Now the CA tools package would give me the sample.split function over here. So let me go ahead and use the sample.split function. So this again takes in 2 parameters over here. So the first parameter is basically the column on the basis of which you would want to split your data. So that particular column would be high because it is a dependent variable, and the split ratio which I'm giving over here is 0.65. That is 65% of these records would have the true value, and the rest 35% of the records would have the false value. And this result, I am storing it in a new object, and I am naming that object to be equal to split tag. Now I'll just show you what is there in the split tag. So I'll actually show you maybe the first 5 results of this. You have true, false, true, true, true. Now this means that out of those, so as you see 65, 0.65, so 65% of the records have been assigned this true value, and the rest 35% of the records have been assigned this false value over here. So now that we have the true and false tags over here, we are going to subset our data on the basis of these true and false labels. So wherever we have the true labels, we are going to select all of those true labels and store them into our training set. So inside this subset function, I am going to give the data set, which is basically car seats. After that, I will specify this, that split tag is equal to true. So from this entire car seats data set, wherever the value of split tag is equal to true, I am going to select all of those records and store them in the train set. Similarly, from this entire car seats dataset, wherever the split tag is equal to false, I am going to select all of those records and then store them into the test set. So now we've got the testing and the training sets ready. Now let me show you the number of rows present in the testing and the training set. So there are 260 rows present in the training set, and there are 140 records present in the test set. Alright, so that was the splitting of our data into training and testing set. So now that this is done, we are again going to build our model. So now the difference is we are going to build our model on the training set and not on the entire data set over here. So I will use the tree function again, and this time this would be the function, right? So the first parameter is the same. So I am passing in the high column, which is our dependent variable, and after the tilde symbol, I'll just put in a dot over here. So this dot means that all other columns except the high column would be my independent variables. And once I given the formula over here, I will given the data on which I want to build this model. So I want to build this model on top of the train set. So yeah, so I have successfully built this model. Now let me go ahead and clear this out, and I'll have a look at the summary of this. So summary of tree model which I have just created. So as you see, now I have only 21 terminal nodes over here, and also I have the residual mean deviance and misclassification error rate given. Alright, so I have built the model. Now let me go ahead and visualize this model. So plot of tree model. Let me again count the number of terminal nodes over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So as you see, there are 21 terminal nodes, which is what was stated in the summary of this. Now let me go ahead and add text to this. So text, I'll pass in tree model inside this, and let me zoom this over here. So again, as you see, the split is being decided on the basis of this shelf location column. Now if I go on to the left side of this, so if the shell location is bad or medium, I'll come on to the left side. Next, I'll be checking if the price is also less than 92.5. So if the price is less than 92.5, I'll come over here, and then I'll check if the population is less than 207.5. So if the population is less than 207.5, again I'll come to the left side and I'll check if advertising is less than 9. And if this is the case, then the result would be no. That is, the sales will not be high. So for the rest of the two cases, it will be yes. Now let me come to the right side of it. So if the shelf location is actually good, then I'll come to the right side of it and I'll check if the price is actually less than 156.5 or it is greater than that. So if it is less than that, then I'll check if the advertising is greater than 6. And if the advertising is greater than 6, then it will be yes. On the other hand, if the advertising is less than 6, then again I'll be on this side and I'll check if the age is less than 55 or greater than 55. So if the age is age of the people in the region is less than 55, then the sales of the car seats would be high. Else the sales of the car seats wouldn't be high. Right, so this is the sort of inference which we can draw from this. So we have added the text, we have visualized it. Now it's time to predict the values on top of the test set. So we have successfully done this, and to predict the values, let me just go ahead and copy this over here and paste this over here. So I'll be using the predict function. Now this predict function takes in these three parameters over here. So the first parameter would be the tree model. So this is basically the model which we have just built, and then the second parameter would be the test. Second parameter is basically the test set on which we want to build the model, and then we will give something new. So this parameter would specify what is the type of prediction that we want, and since we are doing classification, the type of prediction over here will be class. So I have used this predict function and I am storing the predicted results in tree pred. Now I will go ahead and build a confusion matrix for this. So to build a confusion matrix, I will be using this table function. So as you see over here, inside this table function, I'll be passing in the actual values and the predicted values. So the actual values are stored in test $hi and the predicted values are stored in tree underscore pred. Right, so I have created this confusion matrix. Now inside this, you basically have a tabular, you basically have a table, right? And you have this no and yes values over here. So what does this mean actually? So what this tells you is, out of all the records where the sales value was actually no, 66 of them were correctly predicted to be no. And this value tells that out of all the records where the value was actually no, 17 of them were incorrectly predicted to be yes. Then if we come down over here, out of all the records where the actual value was yes, 25 of them were incorrectly predicted to be no. Similarly, out of all the records where the actual value was yes, 32 of them were correctly predicted as yes. So this left diagonal which you see over here, this indicates all of the records which were correctly predicted. And this right diagonal indicates all of the values which are incorrectly predicted. So to get the accuracy, you will basically divide this left diagonal with all of the values present in this matrix. So let me do that over here. So I'll type in 66 plus 32 divided by 66 plus 32 plus 25 plus 17, and we get an accuracy of 0.7 over here. Now let me actually store this in ACC1 over here, and let me actually paste this over here. Right, so I have got the accuracy of this. Now I'll actually show you the plot of this again. Let me also add the text over here. So as you see, we have created a very big decision tree over here, right? So there are a lot of splits and this is a tree which has overgrown. Now the question is this: do we actually need such a big tree to get the right accuracy? What if we'll get the perfect accuracy? Maybe, you know, if we end the splitting at this part or end the splitting at this part. So how do we find it out? So this is where you know, the mean deviance comes in, the misclassification error rate comes in. So you know, there could be a case where if we stop splitting at this particular stage, the misclassification error rate would be the lowest. Or if we stop splitting at this particular stage, the mean classification error rate could be the lowest. So let's go ahead and find that out. So for that purpose, we will actually be building a cross validation for pruning our tree. So we have this cv.tree function, which is again part of the tree package. Now let me go ahead and use this function over here. So this takes in two parameters. So the first parameter is the tree model, or the model which we have built, and the second parameter is the function which is prune.misclass. So we are trying to prune this tree by finding out the right value of the misclassification error rate, and I am storing it into a new object, and that new object is basically cv tree. So now that this is done, right, let me just print out cv tree over here. So I'll just type in cv tree. All right, so just give me a second, guys. All right, so I have successfully given this over here. Now what you see over here is you have size, deviance, you have k value, you have method over here. So we started off with one root node, then we had two root nodes, 3, 5 and so on, and the initial deviance was 107, 82, and the deviance, you know, it kept on decreasing. So this deviance kept on decreasing till 57, but after that, you know, the deviance increased. So this would be the right value of the number of terminal nodes. So this is 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5, 6. So this is where we'd have to stop, right? So when the number of terminal nodes are actually 9, that is when we would have the lowest value of deviance. So let me show you again: 1, 2, 3, 4, 5, 6, and over here you have 1, 2, 3, 4, 5 and 6. right? So at the value of 57, we have the lowest deviance. So let me check that out. So now what I will do is I will go ahead and prune the tree over here. And to prune the tree, I am using this prune.misclass function. And in this prune.misclass function, again, I am passing in two parameters. So the first parameter is tree model, and then I will give the best to be equal to 9. That is, this will end when the number of terminal nodes are actually 9. So now that we have given this, we will store this in a new object and we'll name that object to be pruned model. Now I will go ahead and plot the pruned model over here. So plot of pruned model, and let me show you the number of terminal nodes over here. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So as you see, you have 9 terminal nodes over here. Now let me go ahead and also add the text over here. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We have also added the text over here. Right, so again, the root node, the split is with respect to shelf location. So if the shelf location is bad or medium, we will come on to the left side of this, and then we'll check if the price is less than 92.5. And if the price is less than 92.5, then obviously the number of sales of car seats would be high. But on the other hand, if the price is greater than 92.5, then we'll come to the right side of it, and again we are checking multiple conditions over here. Right, so this is how you can actually prune your tree, and you can figure out if do we actually have to overfit our tree, or we can basically cut out our tree at a particular stage. Now earlier we had got an accuracy of 0.7 with the fully grown tree. Now after pruning this tree, let me go ahead and predict again. So this time the model which I have built is pruned model. So I am trying to predict the values with respect to this pruned model on top of the test set, and the type of prediction is class, since this is classification, and I'll be storing this in tree underscore pred. Right, so I have done this over here. Now again, let me go ahead and build up this confusion matrix. So I'll be using the table function to build this confusion matrix over here. This again takes in two parameters. So the first parameter are the actual values which are stored in test $hi, and then I will give in the predicted values which are stored in tree underscore pred. Now let me check in the accuracy over here. So as you see, this left diagonal would indicate all of those values which have been correctly classified, and the right diagonal indicates all of those values which have been incorrectly classified. So it would be 64 plus 40 divided by 64 plus 40 plus 19 plus 17, and we get an accuracy of 74%, right? So with a fully grown tree, we had an accuracy of 70%, but when we had actually pruned our tree, we got an accuracy of 74%, right? So this means that you don't have to overfit your tree. You can actually prune your tree at a particular stage, and that can give you a much better accuracy than what your fully grown tree can give you. So this is our confusion matrix over here, right? So yep, we are done with our first case study, where we were trying to classify whether the number of sales would actually be high or low on the basis of all of these different columns over here. So now that this is done, we will go ahead to the second part of it. So this, what we did was actually binary classification. Now instead of binary classification, I actually want to do multi-class classification. So to do multi-class classification, I'll be working with the iris dataset. So let me show you the iris dataset over here. I'll type in view, and let me give in the name of the dataset, which is actually iris. So this is the iris dataset over here. So you've got all of these columns over here. You've got sepal length, sepal width, petal width, and the species column. Now, this is a multi-class classification because I am trying to determine the species of this iris flower with respect to the rest of these columns over here. So let me just show you. I'll use the table function, and I'll type in iris $species. So as you see, we've got three different species. So the species of the flower either could be setosa, versicolor, or virginica. And there are 50 species of setosa, 50 species of versicolor, and 50 species of virginica over here. Right. So as I've told you, I want to find out the species of this iris flower with respect to the rest of the four columns over here. So now that this is done, again, I want to divide this entire iris data set into two parts, the training set and the testing set. So for this purpose, I'll not actually be using CA tools. I'll be using the carrot package. So yeah, again, so to build the decision tree, we've got different packages. So either we can use the tree package, or we can use the party package, or we can use the rpart package. So the first example of the first demo was with respect to the tree package, and the second demo is with respect to the party package. So let me go ahead and load up this library. So I'll type in library of party over here. Right, so I have successfully loaded this party package. Now to divide this dataset into training and testing set, I will be loading up this carrot package. Right, so this carrot package gives me the create data partition function. So I'll be using this create data partition function, and this takes in 3 parameters. So the first parameter is basically the data set, the column on the basis of which I want to divide this data. Next is the split ratio. So I am giving the split ratio to be equal to 0.65, and list is equal to false. So if you want the result to be in the form of a list, you'll give in true, but I don't want the result to be in the form of a list. So that is why I'll set the list to be equal to false, and I am storing this result in a new object, and I am naming that object to be equal to split tag. So this is done. Now let me actually show you what do we have in split tag. So split tag, again I'll show you the first 5 records. So what you see is you have 1, 5, 7, 8, 9. So out of these 65% records, right? So these are, so this row number 1, row number 5, 7, 8, and 9, these are part of those 65% records over here. Right. So now that we have the those 65% records stored in split tag, so from the entire iris data set, I will select only those row numbers which are present in the split tag, and I will store all of them in the training set. Right, so this is done. Now similarly, from the entire iris data set, I will select those records which are not present in the split tag, and I will store them in the test set. So now I have my testing and training sets ready. So n row of train, so I have 99 records in the training set, and then I'll also type in n row of test. So I have 51 records in the testing set. So I have my training and testing sets ready. So now I'll go ahead and build a model on top of the training set. So I'll be using the C tree function, which is part of the party package. So in this party package again, so in the C tree function, I'll give in 2 parameters. So the first parameter is again the formula. So I want to determine the species of this flower. So this is my dependent variable. So this is my dependent variable, and the rest of the columns would be the independent variables. And that is why I have given this species column on the left side of this tilde symbol, and I have given this dot on the right side of this tilde symbol. So species column is my dependent variable, and the rest of the columns are my independent variables, and I am building this model on top of the train set, and I am storing this result in the my tree object. So we have successfully built this model. Now I will go ahead and plot my tree. So let me remove this old plot over here, and let me build this up, and let's see what do we get. So this is what we have. So over here, the first split is being determined by the petal length column. So if the petal length is less than or equal to 1.9, then the species of the flower would definitely be setosa. Right, so with a 100% guarantee, you can see that if the petal length is greater than or equal to 1, if it is less than or equal to 1.9, then the species of the flower would be setosa. On the other hand, if the petal length is actually greater than 1.9, then you'll have the second condition. So the second condition is if petal width is less than or equal to 1.7. So if it is less than or equal to 1.7, again you'll have the next condition where you'll check if petal length is less than or equal to 4.7. So if petal length is less than or equal to 4.7, then your species is definitely versicolor. On the other hand, if your petal length is greater than 4.7, then there could be two options. So there's a 59% or a 60% chance that it could be versicolor, and there's a 40% probability that it could be virginica. And on the other hand, if you have this petal width to be greater than 1.7, then you'll just come down to the right side of it, and you can say that with 90% probability the species of the flower would be virginica, and with 10% probability that the species of the flower is versicolor. Right. So we have built the model and we have also plotted the model. Now it's time to predict the values. Now to predict the values, again I'll be using this predict function, and this takes in this three parameters. So the first parameter is the model which you've just built, the second parameter is the test set on which we are trying to predict the values, and then we have the type of prediction, which is basically response, and I am storing this result in my pred object. Right, so we have predicted the values and stored the result in this my pred object. Now I will go ahead and create a confusion matrix again. So the actual values are stored in test $species and the predicted values are stored in the my pred object. So I have successfully created this confusion matrix over here. So let's understand this confusion matrix. So all of those records, so we see that all of those records where the species is setosa, they have been correctly classified as setosa. If we come to versicolor again, all of the records where the species of the flower was versicolor, all of them have been correctly classified as versicolor. Similarly, all of the records where the species of the flower was virginica, so out of those, 15 of them have been correctly classified as virginica, but 2 of them have been incorrectly classified as versicolor. Right, so you have only this part where there is misclassification. In the rest of the cases for setosa and versicolor, there is 100% correct classification. So let's go ahead and find out the accuracy of this. So that would be 17 plus 17 plus 15, which is your left diagonal over here, right? So all of these diagonals are present, so all of these values are present on the left diagonal, and then you will give in the rest of the values, which are 17 plus 17 plus 15 plus 2, and you get an accuracy of 96% with this model which you've just built. Right, now let's understand the problem with this model. So as you see, only 2 columns have been used for the prediction of the species of the flower. So only petal length and petal width have been used, but the rest of the columns have not been used. So that is why we are going to build this model again, where we'll use only petal length and petal width as our independent variables. So I am building my second model over here, and in this species would be my dependent variable, and the independent variables would be petal length and petal width. And I am building this model on top of the train set, and I am storing this result in the my tree2 object. So I have built this model. Now again, let me go ahead and visualize this. So I'll use the plot command and I will pass in my tree2 object inside this, and as you see over here, so this is what you get. So this is sort of the same plot which we've got from the previous one, right? So the only difference is, instead of using all the columns as our independent variables, we have only used petal length and petal width as our independent variables. All right, so this is done. Now we will go ahead and predict the values. So we have built the model. Now it's time to predict the values. So this time I am again predicting the values, where I am passing in the first parameter as my tree2. So this is the model which you have just built, and I am predicting the values on top of the test set, and the type of prediction is response, which I am storing in my pred2. So I have made the prediction. Now let me go ahead and create this confusion matrix. So I am passing in the actual values which are present in test $species as the first parameter, and then the second parameter, the predicted values, are stored in my pred2. All right, so again we have the same result over here, right? So instead of using all the columns, if we just use the petal length and petal width column, that is more than enough for us to determine what type of species this particular iris flower is. That's quite an interesting observation, isn't it? Right, so we are done with binary classification. We are also done with multi-class classification. Now we'll go ahead and do regression with decision tree. And for that, we'll be working with the Boston dataset, and we'll be using a different function. So we'll be working with the rpart library over here. So this rpart basically stands for recursive partitioning. Right, and let me go ahead and load up this Boston dataset. So I'll be using this read.csv function, and I am passing in the path over here, and I'm storing this in a new object and naming that object to be Boston. So let me just type in view of Boston in here, right? So this is my data set. Now let me just show you this data set over here. So this is also part of the mass package. So let me load up the mass package. Now let me put in this question mark and let me type in Boston over here. Right, so this is our Boston dataset, which comprise of all of these columns. So you've got CRIM, which is basically the per capita crime rate per town. Then you've got ZN, which is proportion of residential land zoned for lots over 25,000 square feet. Then you've got Indus, proportion of non-retail business across per town, right? So out of all of these, our column of interest would be this MEDV column. So this MEDV column stands for median value of owner occupied homes in $1,000. So I am trying to determine what is the median value of the house with respect to the rest of these columns over here. So in your free time, you can go through the description of this entire data set, right? So you have all of these columns and you can go through the description of this particular data set over here. So now that this is done, we have loaded the data set, we have understood the data set. Now it's time to divide this data set into training and testing sets. So for that, we would require the create data partition function, which is part of the caret package. So I am loading the caret package first. Once I have loaded the caret package, I am using this create data partition function. So again, I want to divide this dataset into two parts with the help of this. So on the basis of this MEDV column, and the split ratio which I'm giving is 0.70. So I want 70% of the records to be in the train set and 30% of the records to be in the test set, and I am storing this in split tag. Now I will just go ahead and take all of those records in the Boston data set, which are so those rows which are present in the split tag, and store them in the training set. Similarly, all of those rows which weren't present in the split tag, I am selecting all of those rows from the Boston dataset and I am storing them in the test set. So I've got my training and testing sets ready again. So I'll type n row of train, and I see that there are 356 records. Now again, let me type in n row of test. So let me just type in n row of test over here. So I've got 150 records in the test set. So I have divided this dataset into training and testing set. Now it's time to build the model on top of the train set. So I'll be using the rpart function, which is part of the rpart package. So the formula is pretty much the same, right? So the first parameter, I am giving the MEDV column as my dependent variable. I'm putting it on the left side of the tilde symbol, and I am taking the rest of the columns as my independent variables. And I am building this model on top of the train set, and I am storing this in a new object, and I am naming that object to be equal to my tree. So I have successfully built this model. Now I will go ahead and visualize the model which I've just built. And to visualize that, we have this package called as rpart.plot, and this rpart.plot package would give me the rpart.plot function, and I am passing the my tree object inside this. So let me see what do we get. Right, so over here, as we see, the first split or the root node is based on this lstat column. So we are checking if the value of lstat is greater than or equal to 7.7, and if it is greater than or equal to 7.7, then we come over here. Again, we check if lstat is greater than or equal to 15. If this is true, we'll do another check where we are finding out if the crime is greater than 6.3. And if that is true, your median value of a house would be $12,000, and if it is crime is not greater than or equal to 6.3, your median price would be 17. Now let's come to this higher end over here where the median price of the house is $46,000. So let's see how do we get $46,000. So first is your L stat value. So if your L stat value is greater than or equal to 7.7, if it is not greater than or equal to 7.7, then you will come to this side and you are checking if RM is less than or greater than 7.5. So if RM is greater than 7.5, then you'll come over here and you'll say that the median price of the house would be $46,000. Right, so this is the way how you are trying to find out the price or the median price of this house. Similarly, if I want this case over here, so L stat is not greater than or equal to 7.7, we'll come over here. Again, if RM is less than 7.5, we'll come over here. Again, if age is actually greater than 92, we will come on the right side. Then we will say that the price of the house would be equal to $42,000. All right. So we are done with the visualization part of it. Now we will go ahead and predict the values. So we have built the model. Now it's time to predict the values. So this takes in two parameters. So the first parameter is the model which we have just built. The second parameter is the data set on which we are trying to predict the values, which is basically the test set, and I am predicting the values on top of predict tree. So I have successfully predicted the values as well. Now that this is done, it's time for me to bind the actual values and the predicted values. I'll be using the cbind function. So the actual values are stored in this MEDV column of the test set, and the predicted values are stored in the predict tree object which we had just created. So I am binding these two and storing them in a new object and naming that object to be equal to final data. So I'll have a glance at this view of final data. So these are the actual values of the median price of the house, and these are the predicted values of the median price of the house, right? If the actual was 24, it was predicted as 25, actual was 33, it was predicted as 31. So what you see, you basically have an error in prediction for all of these. And if we want to find out the average error in prediction, we have to get the root mean square error, right? Now again, so this is actually a metric. So let me show you the class of this. So I'll type in class of predict tree, and you see that this is actually this is a metrics over. So this is actually class of final data. So I'll type in class of final data. So this is a metrics, and I have to convert this metrics into a data frame. So I'll select as dot data frame. I'll pass in final data into this, and I'll store it in a new object. I'm actually storing it into the same object, which is final data. Now let me check the class. So class of final data. So as you see, this is a data frame now. All right. So now I will go ahead and subtract the predicted values from the actual values, and that will give me the error in prediction. So when I subtract this particular value from this particular value, I will get the error in prediction, and that is what I'm doing. So final dollar predicted, and I have final dollar actual. I am subtracting these two, and I will store the result in something known as error. Now I will bind the error back to the final data which I have. So cbind final data, and I am binding the error to this, and I am storing this in final data. So view of final data. So actual values, predicted values, and I have the error in prediction over here. Now I will go ahead and find out the root mean square error. So this is what I have over here, right? So first I will take the square of the error. So final data dollar error, I will take the square of this. Then I will take the mean, so mean square, and when I take the square root, I will get root mean square error, and I am storing this in RMSE1. So let me show you what is the value of RMSE1. So I get a value of 4.99. All right. So this is my first model, and I've got the RMSE value or the root mean square error value to be equal to 4.99. Now one interesting take over here is we are not actually using all of the columns over here, right? So we are only using LSTAT, RM, age, DIS, and crime. So instead of giving all of the columns, let me just use these particular columns and build the second model. So let me select this over here, right? So I am building this second model where my dependent variable is again MEDV, but my independent variables would be only LSTAT, and then I've got RM, after that I've got age, then I've got crim, and then I've got DIS, right? So have I included everything? I've got LSTAT, I've got RM, I've got CRIM, and age I've got, and I've also got DIS. So I have added all of these as my independent variables, and I am building this model on top of the train set, and I am storing this in a new model and naming that model to be equal to my tree 2. Right, so I have built this model. Now let me remove this actually, and yeah, so now let me go ahead and predict the values. So I'll use the predict function again. I will pass in my tree 2. So this is basically the first parameter, and the second parameter would be the test, because I want to predict the values on top of the test set, and I will store this in a new object and name that object to be equal to predict tree 2. Right. Now I will go ahead and bind the actual values and the predicted values. So the actual values are basically the MEDV column from the test set, and the predicted values is basically this object predict tree 2, and I am naming this as actual, and I am naming this as predicted, and I am storing this in final data 2. Now I'll have a glance at final data 2. So view of final data 2, I've got my actual values and the predicted values over here. Right, now it's time to convert this matrix into a data frame. So I'll use this as.dataFrame function, and I'll pass in final data 2 inside this, and I'll store this in final data 2. Now let me go ahead and calculate the error in prediction. So the error in prediction is basically actual minus predicted, right? So I'll type final $2 actual minus final data $2 predicted, and I will store this in error 2. So I have the error in prediction. Now let me go ahead and bind the error back to the original data, and I am storing this in final data 2 again. All right, so view of final data 2. So I've got the actual values, the predicted values, and the error in prediction. Now let me find out the root mean square error for it. So I'm taking the square of the error, then I'll take the mean of it, then I'll take the square root of it, and I'll store it in RMSE2. So let me print out RMSE2, which is 4.99. Let me also print out RMSE1, which is 4.99. So as you see, this is basically the same. Now instead of including all of the columns, if we just include these columns, we'll get the same particular result. So that is why you don't have to overfit your model. It's not necessary to build your model on top of all of the columns. So by visualizing, you got to know that if I just include these particular columns, then I'll get the same sort of accuracy, or I'll get the same sort of error in the model which I'm building.
Decision tree is one of the most commonly used algorithms in the world outside, in the practical world. For some reasons, as you will see down the line, though it may not be one of the best algorithms under all situations. Under some situations, you will see that your logistic regression probably gives you better results than decision tree. But still, there is something about decision tree which makes it stand out. So let's see what does that do, something about decision tree. And before I go too far, there is no one single algorithm which is considered as the best algorithm. In production, we might use a mix of algorithms, put them together in one group. That group is called an ensemble, a French word, and we put that group as one single model. The ensemble technique will be covered tomorrow. We'll cover that tomorrow. Okay. So don't be under any impression that this algorithm is better than that algorithm. There's no such reality. Some algorithms perform well in some situations. Other algorithms perform well in other situations. So we always use a group. Have you seen decision tree before? People who come with a lot of experience, management experience, decision tree is a very standard management tool. that is used under certain specific conditions. Can you tell me what the conditions are in which we use decision trees? What could be those situations where they use decision trees? In fact, decision trees used in our day-to-day life, we all use it every day. What should be our strategy? How should I, so that minimize my risk? Yeah, it is a kind of flowchart, if else. It helps you to take decisions in those situations where multiple states are possible and you don't know what's going to happen. You want to minimize your risk. So decision tree is one of the standard techniques that is employed to decide what action to take, what sequence of steps to take. People who have used decision tree, you'll find a lot of similarity between what I'm going to do and how it has been used already. Shall we look at this now? Decision tree. Let me give you, for people who have not been exposed to decision tree, some brief idea about what this is. It can be used for classification as well as regression. The most of the time it is used for classification. Since you people have done a linear model, what is the data set on which you build a linear model? Was it MPG, miles per gallon data set? Was it? Cars, miles per gallon? What is the accuracy you got? Overall accuracy? 74%, 75, 76, that's the range in which you will get for that particular data set. Miles per gallon data set, the linear model will give you in the range of 74 to 76. Use decision tree on that. It will give you 85+% accuracy. A phenomenal jump in terms of accuracy percentage, 85% plus. Right? That is the beauty of this. So it can be used for classification, it can be used for regression, both. Mostly used for classification. It consists of what we call the nodes and the branches, where the nodes represent some decision you're taking or some functions you're going to execute, some logical functions. Those functions will be executed on your independent attributes, the columns in your data frame. People who have not seen decision tree earlier before, this is the overall structure of decision tree. It can continue to any level. I'm just showing you some few levels. This is called the root node. All the things which are in what is the shape called? Oval. All these oval shapes are my nodes. Nodes represent any function call that you're going to make on your independent attributes. The result of the function can be this or this, binary result, true or false. So this is the result of the function executed here. These are the results of the function executed here. So at each node, we execute a function. All these are functions. This one is called the root node. And all those nodes which are not further divided, they are called leaf level nodes. LEAF, leaf. In between the leaf nodes and the root node, you have these function nodes. The algorithm that we are going to use, it is called CART, Classification and Regression Trees. CART, Classification and Regression Trees. It is a binary tree creator. It creates only 2 branches in every node. There are some commercially available algorithms which can create multiple branches at each node. You might be wondering why 2 branches? Why not 3 branches? There are commercial algorithms available, but the one which we use in scikit-learn, it is open source. It is called CART. Some of you might be wondering, that means it can be used only for binary classification. A decision tree can be used for character recognition in your English alphabet. How many characters are there in English alphabet? 26. You can use decision tree to classify those characters into 26 classes. So what will happen is it will do A versus others, B versus others, C versus, it will convert into binary. So it can be used for multi-class classification. It doesn't have to be binary class only. Just because the nature of the algorithm is to split it into two every time does not mean it can be used only for binary classification. It can be used for multi-class classification. All right. What happens is at the leaf level, the nodes are of three types: root node, branch nodes, and the leaf nodes, the three types. At the branch nodes, we have the functions and then the result of the functions. Root node represents your entire data frame, data set. Suppose you're using decision tree for classification. You're going to classify things. For classification problem, whether a given record, whether a given image belongs to an airplane or a ship or a zebra, you want to classify a given image into one of these three categories. What decision tree will do is it will tell you the probability. The probability that this is an aeroplane is 70%. Probability that is a zebra is 2%. Probability is something else is 30%. And it will give a percentage. Those percentages are given at this level, the leaf level. Those percentages are called posterior probabilities. By any chance you covered probability-based analysis like naive-based? Not yet, right? So there we'll talk about something called posterior probability. When you do those analysis, you'll be talking about prior probabilities and posterior probabilities. Posterior means after knowing all these things, what is the probability that this belongs to a particular class? Hence the name posterior. I think it's voice operated.
Hello?
Yeah, there you go.
So the question is, what do we mean by leaf node belongs to the majority class?
So what happens is, suppose you have a data set. For simplicity's sake, let's take only two classes. Okay, I have a data set here. And these are independent attributes, I1, I2, I3, so on and so forth. And the target variable is a class. Okay. In the class, there can be two types. One is defaulter, other one is non-defaulter. Defaulter, non-defaulter. You're working in a bank. The management in the bank has asked you to create a model where the model should take as input the parameters about the various customers, the income, the age category, where the person lives, so on and so forth. And the model should tell you what is the probability that this person will be a defaulter versus non-defaulter. All right, all of you with me? Okay. So the bank gives you all the historical data of people who have taken the loans. Some of them were defaulters, some of them were non-defaulters. Till now, are you all with me? Okay. Now, when you create a decision tree, what happens is all this entire data set is used at your root node. There's a lot of detail to it. I'll come to those details gradually. And then, based on some function which is executed on one of these independent attributes, your data gets split into two. When the data gets split into two, here also you have some records, here also you have some records. Find out what is the majority here, defaulters or non-defaulters. Find out what is the majority here, defaulters or non-defaulters. Suppose the majority here is defaulters. Then this node gets the label of defaulters. Suppose the majority here is non-defaulters. This gets the label of non-defaulters. But please understand, it is not 100% non-defaulters. It is not 100% defaulters. It's a mix, but the majority is this. All right. Since it's still a mix, majority is this, I apply some other function on some other attribute on this data set and further split it. So this small data set gets further split into smaller set. And in this data set, suppose all of them are only defaulters. Then this node does not need to be split any further. It's already completely known. So I know that when somebody follows this path, he is likely to be defaulter. So I don't need to further split it. On the other hand, this one has still got some mix of default or non-defaulters. Suppose the majority of them are non-defaulters. So on some other function which is executed on one of the other attributes, this data will be split again. And suppose the split is such that all these are non-defaulters, all these are defaulters, then you don't need to further split this. Now I know under what combination can a person become a defaulter. Maybe this combination of functions, this combination of functions. So at every node, you'll find out what is the majority class. The label of the majority class will be assigned to the node. But the fact is, unless you're at the leaf level, whenever you're in between the leaf and the root, the nodes will always be mixed. They will be contaminated. They will not be pure nodes. We want to reach a stage in our decision tree algorithm where we have pure nodes. Pure nodes means nodes which belong to complete defaulters only or non-defaulters only. When I reach that stage, then I know under what combination somebody becomes a defaulter, under what combination somebody becomes non-defaulter. So I know all those combinatorials, if I may say so, which lead somebody to become defaulter, and the other combinatorials which lead somebody to become non-defaulter. This is the pattern I'm looking for. This is the model I'm looking for. What we call linear models, which finds out the best fit surface for you, best fit line for you, which expresses the relationship between the independent variables and the target variable. The decision tree expresses the relationship between independent variables and the target class using these paths. The paths tell you how these independent variables are related to the target class. That is my model. And the beauty of decision tree is, well, not in scikit-learn, in the other language R, I can convert this whole decision tree into English rules. So I'll print out rules for me. If the person's income group is this and his age is that and his education qualification is this, very likely he's going to be non-defaulter. That English rules I convert into Java code and deploy it as my model. There's much more to it than what I've told you. I'll take you through the details, but to answer your question, that is what this means. All right. So if we are doing classification, then the objective of decision tree algorithm is to create as pure nodes as possible. Pure. Pure means the nodes should belong to only one class. That is the objective. In case you are using decision tree for regression, calculating the miles per gallon values, then the objective is at each node, the variance of the data points should be minimized. Now look at this. All of you know what is variance? What is variance? What is variance? Don't give me the formula. I'm not asking for formula. Understand the concepts. Variance is, on an average, how dissimilar two data points are. Variance means, on an average, how dissimilar a data point is from the central value. Xi minus x bar raised to power 2 divided by n. That is what we call variance. So you underroot it, it's called standard deviation. All these are nothing but a way of expressing how dissimilar a point is from the central value. All of you okay? The objective of the decision tree is collect all those records into the different cells such that the variance within a cell is minimized. All similar records come together in a leaf level. The variance within the cell is minimized. Right? It might sound slightly Greek or Latin to you right now. When you go further down the road and do some hands-on, bring up all these questions that are probably bothering you right now. This Gini index, this is called entropy index. I'll show you pictorially the relationship between the two. What you see here in the red dots, these red dashes, this is the curve which represents the Gini. Gini ranges from 0 to 0.5. This is probability 0 to 1. Whereas entropy goes from 0 to 1. That is the only difference between these two curves. If I scale down the entropy curve, I scale it down, then this gray curve represents entropy scaled. And as you can see, between the two, there's not much difference. Between the red and the gray, there is not much difference. Gray represents entropy, red represents Gini. You can use any of the formulas, they give you the same result. The green one, we don't use in decision tree, so I'm not going to talk about this. This is more related to your confusion matrix. If you guys have done confusion matrix, have you done confusion matrix? Yes. It's related to that. Oh, you're going to say something. Oh, yeah, okay, good.
It touches 0.5, right?
0.5.
Does it mean that is the level at which we should be using Gini? Or if the impurity is more than that, we won't be able to use that Gini index formula there? Or
No.
what does it signify?
No. These are two ways of measuring your impurity. Okay. Entropy the impurity ranges from 0 to 1. Gini, when you use Gini formula for measuring the impurity, it ranges from 0 to 0.5. 0.5 is the maximum impurity in Gini.
Okay.
Right? So there are two different ways of measuring the same thing. One maximum is 0.5, the other one is 1. And one more thing, it's important that I bring it out here itself. This relationship between probability and entropy going to 1 and going to 0.5, this will hold only when you have two classes, one versus others. When you have three classes, then this bar will go further up. This will go further up. Okay. I don't want to confuse you with that. So right now, let's keep it out of the picture. But keep this in mind. This relationship and the scale is true only for two classes. One versus other. A versus other, B versus others. Those kind of things. We call it OVR. OVR stands for one versus rest. You will see this when we run the algorithm, OVR strategies. These are the different decision tree algorithms available. C 3.0, it's also called ID3, iterative dichotomizer. Very old, we don't use it anymore. C 4.5, it came over with some limitations of ID3. Our cart is based on this. In Python, the cart algorithm is based on this. C 5.0 is the latest available commercial version, not open source, so we can't use it. In Python, we have implemented as cart, which is nothing but C 4.5. C 4.5 is open source algorithm. Advantages, disadvantages, all algorithms have advantages, disadvantages. The advantages of decision tree is simple. You don't need to know high-fi statistics. You don't need to worry about the p-values and all these things. Simple. It's very fast in your production environment. Classifying. Why is it very fast? Because the algorithm slashes your uncertainty by half in the very first level. So every level, it slashes the number of records you have to check by half, right? So its performance is very fast. It does well with noisy data and missing data. It does well with missing data. It treats missing data as another category. You don't need to process it. It does well with noisy data is something which I take with a pinch of salt, because this is what you will come across when you read in books and articles. but none of the algorithms can really handle noisy data, honestly. And as I told you, decision tree, even a slight change in the distribution of the underlying data set can change the tree structure completely. So I really you have to take this with slight pinch of salt, but this is true. It can handle numeric and categorical variables. You don't need to have very high-fi knowledge of statistics or mathematics to implement to make use of decision tree. The formula which I showed you is only conceptual. You don't even need to know that. Disadvantage, there are some disadvantages which we need to be aware of. As I said, it's biased towards those columns which have large number of cardinal values in them. Why? Because that gives the decision tree that much more room to experiment. This algorithm may not be very optimal in modeling relationships because this is an access parallel algorithm. Let me tell you what it means. Simple, nothing to worry. Are you all aware of the feature space? Have you heard of this word feature space? Feature space? Okay. Last session means the first half? First half. But you've not heard of feature space before that? Nothing. Okay. All right. See, now you have a data frame with you. You have a data frame. And in this data frame, let's assume we have 3 independent variables and 1 target variable. I1, I2, I3. And all these are various values. Suppose the value here is 5. Suppose the value here is 7, 3. And the target value is some MPG, some 50. Then you have another variable here, 10, 2, 1. Then 15, 3, 6, something of this sort. And you have various values here, 20, 13, so on and so forth. This data frame, whenever you learn any machine learning algorithms, all machine learning algorithms are taught in the context of a virtual concept which is not real. That virtual concept is called a feature space or a mathematical space. Now these 3 dimensions which you see here, this is your I1, maybe this is your I2, this is I3. The independent variables become the dimensions of this mathematical space. We call this data vector, okay? This is called a vector, data vector. Now look at this, 5, 7, 3. Maybe 5 on this, 7 on this, and 3 on this. Wherever these points meet, 3 on this, wherever this point, this data, this blue dot represents this record. Similarly, when I plot this 10 to 1, 10 on this, 2 on this, and 1 on this, wherever these points meet, this blue dot, it represents the second record. So every record in your mathematical space becomes a dot. Every record in your data frame becomes a point in the mathematical space. All right. So now let us assume, hey, you guys have done best fit model? Linear best fit line model? Say yes or no? Yes. Okay. When was this? Last residency. All right. So you have this mathematical space. In this mathematical space, you have data points scattered over. Okay. And you said you did it for MPG, right? MPG versus weight of the car. Maybe you have the third dimension. Let's take it as one dimension right now. Otherwise, you have weight of the car, the acceleration, your horsepower, you have various other attributes. Let's imagine it's weight of the car. Okay. Now, this weight of the car has some distribution, and this MPG has some distribution. The best fit line that you found, the best fit line will always go between the X bar and the Y bar. Wherever these two meet, your best fit line will always go between these 2 points. The best fit model, the linear model which you came out with, will always go through the point where the X bars and the Y bars meet in the mathematical space. And that will be a hinge point. That will be a hinge point. Okay, that will be the hinge point. Okay. Why am I showing this to you? We are in decision tree. In decision tree, what happens is it's something slightly different. Linear model, it gives you a best fit line by reducing the sum of squared errors. Now look at what decision tree does. We are into classification. right now, but we can do regression also. So first, let me explain classification to you. In this, imagine you have two classes, right? Imagine you have two classes where the classes are like this. You have been asked to build a decision tree based model which separates these two classes, the defaulters and the non-defaulters. So the first thing that you do is, suppose I take income. This is income. Your model says, if the income is less than some amount, the node which you get is most likely to be defaulters. Income greater than some amount, the node says likely to be non-defaulters. Though in reality, it's just the opposite. Right? In reality, is just the opposite. So, what your model saying is, if it tries to drop a perpendicular line, it tries to break your data into two sets by dropping a particular line at a particular threshold. It says anybody less than this is defaulter, anybody more than this is non-defaulter. Look at this. When you start with the original mathematical space, you have the root node. Root node reflects the entire data set. Maximum entropy. This entire data set is then further broken into two, where you say income less than some amount, you come to this, or greater than some amount, you come to this. So it drops a perpendicular line here. Income less than this, defaulters, majority are defaulters, greater than this, majority are non-defaulters. So this node is non-defaulter, this is defaulters. But you're not happy because there's still some mix-up, heterogeneity. Then you look at age. You say that people who are a certain age, say for example, I take this age, anybody above this age is likely to be defaulter, anybody below this age is likely to be non-defaulter. So look at this node. This node gets based on age split into all these are defaulters, non-defaulters. This block which you see here, this is this block. This block that you get here, this is this block. As you can see, this block is perfectly homogeneous. It doesn't need to be split any further, but this block needs to be split. So I'll put I can't show you more than 3 dimensions, but I'll keep on putting boundaries which are parallel to the axis. That is why it is called axis parallel algorithm. It puts boundaries in a mathematical space to separate out the reds from the blues. And in the process, you keep getting these nodes. Each one of these nodes is a particular compartment in the mathematical space. But as you can see, when the distribution is angular, decision tree will find it difficult to separate the two. Whereas, if you had used linear classifier will simply put an angular line and get much better results than decision tree would. You'll need a very complex decision tree to get the same accuracy which a simple linear model will give you. That is a limitation of the second point here, may not be optimal as it is axis parallel modeling.
Say if the leaf node is going to have only one class.
Yeah.
So why should we need to do the predict prob here?
No, she wants in probability values.
It's fine, but if that leaf is going to have it's going to have only one class, what is the purpose of doing probability there? It's going to be 100%, right? Anyways, if it is a mixture of red and blue, then I can say that I can call it a probability.
Yeah. To answer this question, you just have to wait for 2 more slides where I will talk about this line. Large trees can become difficult to interpret, and I'll talk about this, elaborate this, and get your answer to that. We'll do that. Just hang on for a minute. His question is, if at the leaf level I have perfect homogeneity, why do I need probability? That is what your question is. It makes sense? Just hang on. No. Actually, it's a beautiful question. It's just come a bit early, so we'll take it up. So can I say that uncertainty is a function of heterogeneity? The more heterogeneity there is, the more uncertainty there is. Can I say that uncertainty is inverse of homogeneity? Homogeneity is also known as purity. Homogeneity is also known as purity. So when you're studying decision tree, you'll come across two words. One is called heterogeneity, which is also known as entropy. E-N-T-R-O-P-H-Y. You'll come across a word called entropy. Some people put a H, some people don't. And then you'll come across purity. P-U-R-I-T-Y. Two words. Entropy and purity, they're opposite to each other. Let me play one more game. Okay, we'll not go too far into this. I'll give you 10 chances. You have to guess which famous personality I'm thinking about. You have 10 questions to ask. Okay, first question Sairam asks. What is the question? Male or female, gender. What did you ask? All right. So look at these two questions, Indian or other nation. I'm thinking of a personality, famous personality. The famous personality can be from anywhere across the globe, right? So if I say not Indian, then you're left with so many other personalities across the globe to look for. We don't know which one. He asked a question. The question was male or female. The moment I answered that question, half of your uncertainty is removed. Whereas the moment I asked that question, a part of uncertainty is removed. So in decision tree, what this algorithm does is, it tries to ask that question, the first question, in such a way that it minimizes the drop in entropy is maximal. So the decision tree algorithm is built in such a way that at every level, it tries to ask a question just like you asked a question to me, resulting in a maximum drop in entropy. So let me give you detail about how this is done. We'll see that. Yeah. Good. Half of the entropy is gone. So this is an experiment which I was trying to do. You have a bag full of color balls. This bag is covered inside a cloth bag, and you're asked to pull out one of these balls. You don't know which ball is going to come out, and each ball, each color can take you to different situation. So you don't know what situation you're going to end up in. Maximum uncertainty. On the other hand, if I give you a bag like this, and I ask you to pull out the ball, you know what color it's going to come. There is no uncertainty. In short, heterogeneity means entropy. Homogeneity means zero entropy.
Broken up in a decision tree, and can we safely assume that the function is applied so that the entropy has gone down to the maximum extent possible when that function was applied at that node?
I'll answer that question in a while. Just hang on. Just hang on. Okay? All right. Now, I will give you one fictitious example. Don't think too much about this example. It's a fictitious example. Data set is borrowed from the world of big data, where I used to work in big data. This is a sales data set. Okay? It has various columns in it. One of the columns is order priority, order number, location, and all these things. In this data set, there's one column called province. This province is the place from where the person has placed the order for you. You're working in maybe the retail giants. You're a data scientist working in one of these retail giants. And the task assigned to you is, can you build a model which, by looking at the various other attributes, will help me decide where is this customer located. So the last column is the location column. The screen size is limited, so I've shown you only a subset of the data set. Otherwise, this is a long data. So in the last column, you have values like some values here, Bisin Nagar, Adyar. Then you have other triplicates. You have other things over here in the last column. Okay. Now the objective is to find out, looking at the other attributes, can I guess where my customer is located? Okay. Since the target column is the last column, the target column is equivalent of the bag which I showed you on the previous slide. The fact that this target column has mix of various localities in the original data set, some records are from Adyar, some records are from Besant Nagar, so on and so forth, it represents the different color balls that you saw here. This is the situation you are in when you take the entire data set, and this is the target column. So this target column is the bag. Are you all okay? Are you all with me on this? What this decision tree algorithm cart will do is, it will find out for you amongst these independent columns, it will select a particular column. And within the particular column, it will also select the breakpoint. When it breaks the data in that column at that breakpoint, it results in two smaller files. These two smaller files are your two nodes. The child nodes, each one of them is one single file. But in the process of doing this, what you have achieved is, whatever entropy was there at this column, that entropy, when you look at these two columns, the sum of entropy of these two columns will be less than the entropy of this column in the original file. The entropy of the target column in the child nodes will be less than the entropy of the target column in the parent node. Then it's still, okay, this majority is some class, this majority is some class, but it's still a mix-up. It's not pure. You've still not got 100% purity. Then in that case, what it'll do is, it'll take this file, this node, and find out again one of these independent attributes, based on which it will break that node into two smaller nodes. So this node is this node is this. Now what happens is, the entropy of the target column at this level will be less than the entropy of the target column at this level. The entropy of the target column at this level will be less than the entropy of the target column in this node. So the objective of decision tree is to break your data into smaller and smaller sets in such a way that the entropy of the target column in the child nodes is less than the entropy of the target column in the parent node. This is exactly what we do when we play guess the personality in 10 questions. This is exactly what we do.
Sample size like 30 or 40. Let's I'm just guessing it. Right? I think probably making a decision tree at a certain level is probably simpler or so. But when you come up with the actual data, the much larger population, right? So breaking that in terms of this entropy and decision. So what I'm saying, my question is more on, have you seen predictive behavior on that, or something like when you do with a larger sample, like the decision tree totally changes somewhere else?
All right. He's asking a question which actually we are many light years away from answering, honestly. We need to actually get some more concepts in place. But to answer his question, decision tree, one of the limitations, weaknesses of decision tree is, from the same universe, from the same population, you take two random samples. Create decision tree on one. Create decision tree on the other. The two are likely to be different from each other. Decision trees get easily impacted by the variance in the samples. Hence, when you're using this algorithm, it is very important to make sure that your sample is a true representation of the population, which is true for all the algorithms. But decision tree is more sensitive to those variances. Right? Man, that sounded like the perfect Greek. All of you know what is sample, what is universe, and all these things? Yes or no? Yes. Okay, what is the difference between the two? The sample and the universe? What is the difference? Psychoth, population is constantly changing. I like that. Yes, you're right. Okay, all right, you're right. Sample is a subset of population, but very important point. You raised your hand. You want to say something? You. No, okay. A very important point. Please keep in mind. Population is dynamic. It's constantly changing. 2 weeks ago when I came, not 2 weeks ago, maybe a month ago when I came from airport to this place, there was no construction activity going on that road. And the route he took was totally different also. But today we got stuck in that mess on the way from airport to this place. Okay. So imagine you're working in Uber, you're a data scientist working in one of the taxi services, and you have been assigned with the task of creating a model where the model predicts the moment somebody sits in a taxi starting the ride, what time he's likely to reach his destination. That's what happens when you sit in the taxi. Even before the taxi starts moving, it tells you by what time you're likely to reach your destination. But in school, I was told that time taken is a function of distance by speed. This guy has not even started and it's telling me time. How does that happen? Welcome to the world of data science. What these data scientists have done is they have taken data from the past of whatever customer engagements and built this model for you. But this data which they have taken from the past, this is a sample. On this, you built the model. What about the data which is being generated at this moment when I'm testing the model? That is not part of this model. That is why we say universe or population is always dynamic. It's not only large, it's dynamic. It keeps changing. Whereas your sample is not only small, it's static. And this brings in a problem into data science. The problem is, the root cause of the problem is, your sample can never be true representation of the real world data. You might have a big data set up on cloud somewhere on AWS, terabytes of data, but still it's a sample because it's static. So that is a huge difference between the two. It's not just the size, it's also the fact that universe is dynamic, live, the data points keep continuously being generated, and new features, new attributes are coming into play, which is not reflected in a sample. That is why, whichever algorithm you use, you have to make sure that your sample is as good a representation as possible. And one of the algorithms which is very sensitive to these differences between sample and the universe is this: preventing overfitting through regularization. This is a very important concept that you will have to be aware of when you're using decision trees. Decision trees are known as non-parametric algorithm. What do you mean by that? When you built a linear model, y equal to mx plus c, in that model, what are the parameters you have? M and c are the two parameters you have. Using the M and C, the algorithm gets for you the best fit line, which gives you the minimum sum of squared errors. Are you all okay? Alive? Yeah, great. Right? So it controls the M and C to find the best fit line for you. We don't have any such parameters in decision tree. We don't have any parameters which the decision tree algorithm learns from your data. Hence, it is called a non-parametric algorithm. So what happens is, when you make use of a decision tree, the decision tree will happily go and create a massive tree for you, which represents many of these cuts in the mathematical space, such that inside each compartment, you have only one record. Each compartment being one leaf. In each leaf, you have only one record. That's the question he's asking. But such trees, when you take into production, they fall on their face. They give you 0 error in training set, but in test set, their error will be very high. We call such trees overfit models. Have you heard of overfit, underfit, and all these things? Are you aware of these concepts? Fantastic. So the decision tree, when it has only one record at leaf level, perfectly homogeneous, 0 error in training set, but that tree is useless as a model because in the test data or in production, it will not survive. So what we do is, we roll back those leaves upwards. That is called post-pruning. We chop the trees and we roll back those leaves upwards. That concept is called regularization. You would have come across regularization in linear model also. If not, probably you will come across these later. That is called the lasso and the ridge regularization. Lasso, lasso, and ridge, RIDGE. So when I apply the regularization on my trees, because I want to productionize it, then at leaf level, you will not find 100% homogeneity. There also you'll find mix-ups. So when you have mix-up, we can make use of probabilities. Hey, use a mic. You should stand here and then you'll know why we need that. Yeah, go ahead, shoot. That's what will happen. So you go and visually analyze your tree. You will see that at leaf level nodes, you have one record in each leaf, 1, 2, and so on and so forth. That means you're in the overfit zone. And as a data scientist, I will never put an overfit model into production. I'll have to roll it back up. To roll it back up, I use what is called post-pruning. So when I do that, I'll end up with a tree with leaves which have mix-ups. They're not homogeneous 100%.
One step above homogeneity is where you stop.
Maybe 1 step or 2 steps, I don't know.
Okay. That
Depends on the situation.
post-pruning situation.
In fact, that question brings me to another point which I'll discuss with you. Let me take these two, then I'll come to that. Yes. In fact, I was going to take the same question up. How do you know at what step you should chop the tree and not more? Okay. This is applicable to all the models, not just decision tree. How do you know how much should you regularize? Whenever you build your models, you always test your model both on the training set and the test data simultaneously. Beginners to data science, the mistake that they do is they try to build a model. I caught you again. I caught her again. Am I that boring? Much more. Okay, no problem. Hey, you want to grab a cup of coffee? I don't know whether it's allowed inside. It's not allowed? In Bangalore, it's allowed. Thank God. Okay. What was I talking? Yeah. Yes. Regularization. Whenever you apply regularization on any technique, you should know how much to apply and how much not. Okay. So whenever you build models, the beginners to data science, the mistake that they do is they try to build a model which gives 0 errors in your training set. That is a mistake that you should never do that. You should always allow the models to do errors in your training data itself. What your objective should be, minimal errors in the production, which is represented by the test data. Your test data represents the production data, which your model has not seen. Your objective should be to minimize the errors in the test data, in the production, not in training. Usually you'll find the accuracy that you get in your training environment, the controlled environment, is more than the accuracy that you get in production environment. You'll find that. It will often happen. 95% of the time, this is what will happen. Your model is giving you 95% accuracy in your controlled environment. When you take it to production, it becomes 90%. It will never happen the other way around, wherein your control environment is giving you 95%, in the production environment is giving you 98%. Very unlikely. What should not happen is, in your controlled environment, 95%, in the production environment, 80%. That should not happen. That sudden drop in performance indicates that you're in overfit zone. So what we do is, when we build the models, we test the models both on this is my complexity of the models. Complexity is also a function of number of dimensions or attributes. It also includes whether your model is a simple linear model, quadratic, cubic, those kind of things. I check, this is my error. I check my training error and my test error both. Okay, I keep building my model. I run it on training data. This is training. And I also run it on test data. You'll often find that as you increase the complexity of a model, your errors come down. But after some point, the test error starts going up. Your training error comes to 0. After some point, your test error starts going up. Your training error starts going towards 0. That point, this is called overfit zone. This is called underfit. Right fit is somewhere in this. So when I build a decision tree, a non-parametric algorithm, it creates a very complex tree for you. You'll see this when we do the hands-on. I will show you that that particular tree on training set, it gives you 0 errors. But on test set, the errors jump significantly. You are in overfit zone. What should happen is that model, whichever model you build, should give you more or less similar accuracies in both your training and in your test. Such models are likely to generalize in the production. All of you okay? So decision tree, we will have to prevent overfitting. We will have to do it. Whenever you're reducing decision tree, you have to do regularization. It does not assume any kind of linear relationships between independent and target variables. It is non-parameterized algorithm. It does not have any parameters to find the best fit surface for you. If left untouched, the decision tree will create a very complex, uncontrolled model for you, which will be overfit. To avoid overfitting, we will have to use regularization. I'll show you how to use that. And for that, we will use certain parameters. Those parameters are called hyperparameters. In modeling, there are 2 types of parameters. One is M and C. These parameters are called model parameters, which are learned from your data set. There are other set of parameters which are called hyperparameters. They are used to control the behavior of the algorithm. Long time ago. I can make out. Where are you stuck? No. Hey, Ram. Not only Ram, anybody. If you have any problem, don't hesitate to ask. Don't get left behind just because you think it's not right to ask. Don't feel that way at all. Where are you stuck, Ram? I'll come to you. This one. All right, just hold on. How about your neighbor? Where's your nameplate, sir? The chair is blocking it. Shiva. Yeah. You're also stuck somewhere? You're with me? 100%. Yeah. Ram, then you can bank on him. Right? Good. But Ram, feel free to ask. Don't hesitate. You had a question. Regularization. What do you want me to repeat on regularization? Okay, no problem. Yeah, sure. Let's do it. Let's start from here then. We have to plot error versus complexity of model. We should always do this. For the time being, you imagine complexity is equal to the number of dimensions, attributes you use in your model. Complexity can also be y equal to mx plus c versus y equal to m1 x1 plus m2 x2 square plus c. That is also another way of bringing in complexity. So I'm looking at the first one, where you keep on adding more and more dimensions to your model. That way you bring in complexity. Okay? Whenever you build your models, you will never get the best model in the first iteration. At least this has never happened to me. You'll always get your models in multiple iterations. The best model which will survive in the production world and give you the results, you'll find that model only after iterations. So in first iteration, I might take MPG versus weight, acceleration, and something else. In the second iteration, I might drop acceleration and take weight versus horsepower. In the third iteration, I might say, okay, horsepower and weight, they are linearly related to each other. Let me combine them into one and use that one dimension for my MPG. So I might iterate through all these things before I finally settle down for a model which gives me good results. All these iterations that you do is what is shown here, moving from simplest model to complex models. Every iteration, I do a test against both the training data and test data. Let me show the test one in the red. Okay. So this is my test. I'm deliberately showing tests slightly higher than training because usually when you break our data into 70-30, you broke your data into 70-30? You gave more data for learning, less data for testing? 80 for training, 20 for testing? Yeah? Obviously, it makes sense. Okay. You give more data for the algorithm to learn from and less data for the algorithm to test on. There is a very basic assumption you're making here. I'm not sure whether you're aware of this. When you prepare for your board exams, the reason I'm giving that example is my daughter recently took the board exams. The more the training set she has, more sample questions she has, more likely she is going to perform well in the board exam. Right? So in the board exam, she is going to get only a few questions, 20 questions, but she should have prepared herself from thousands of questions. So we assume that the 20 question patterns will be somewhere here in this 1,000 question patterns. Are you all with me? So if she's done this 1,000 well, this 20% questions would be a subset of this 1,000. The patterns would be a subset of this. That is what our assumption is. But in data science, this assumption is always many times violated. When I break my data into 70-30 or 80-20, some part of the 20, the patterns in the 20 is not there in this 80, is not there in the 70. Those patterns your algorithm doesn't know. Right? Now you're going to check this model onto this test data. In the test data, there are some patterns which this model has not seen before. So it starts giving you higher errors in your test sets. But what you will see is, as you increase the complexity of the model, you will see that both the training error and the test error, they keep falling down. They decrease. But what you will notice is, after some point, your training error keeps going down, your test error goes back up. This point where the training error starts deviating upwards, this is my best fit point. This side, I'm in overfit zone. My model will give me 0 errors in training. My daughter will give me 100% score in all her sample questions. But in production, in her board exam, she'll bomb. Right? Fortunately, that didn't happen. So she's in overfit zone. Same way, underfit is also not good. Underfit is suboptimal model. Overfit is useless model. You have to be somewhere in between, the right fit model. You're explaining the same patterns, same 20 questions now. Same patterns, that's what you do. Yes, sir, very good. Yeah, there is a concept. Absolutely, there is a concept. That's what I'm telling you. That happens when, okay, there is a concept behind this. Okay, let me finish this off. What time is the tea break? Is it 3:30 because it is 3:30 now, or is it 3:30? It's 3:30? Anyway, Piyush will come and knock the door, so I guess okay, that's okay. Coming to your question, Saikat, there is a theory behind this. There's a concept behind this. What happens is, when you're in the overfit zone, your model is flexible, it's trying to adjust to all the distribution of the data points in the mathematical space of the training set. Let me explain this to you. So this is my mathematical space. This is my independent attribute I1. This is my independent attribute I2. And my data points are distributed like this. There are two classes, and the data points are distributed like this, somewhere like this. I want to separate these two classes. Okay, you build a model, a simple decision tree with only two attributes. It's not a good decision tree. Will not give you good results. So I make use of a non-linear model, and I draw a very complex surface like this, which cleanly separates the blues from the reds. Believe it or not, this surface can be represented in mathematics as an equation. You must have heard about Fourier analysis if you guys come from that background. Fourier analysis can build a very complex function for you, and the model will give 0 error in testing and in your training. When I take this model onto another mathematical space, the test data, in the test data, these blue points and the red points might be distributed in different ways. They might be different in positions. They might be in different positions. It's not guaranteed that it will be the same positions. Now, when I take this model as it is, and transform it here, assuming it goes something like this, your model is going to give too many errors. Can I take the liberty of showing you something? We'll be slightly deviating here so that you get the concepts in place. It is connected to the regularization concept, which I'm going to talk about in decision tree. This is 2-dimension, and this is the nature of your universe, your population. Data points are being continuously generated around the central values, and your data points keep on increasing in volume. Okay. What also happens in the universe is new attributes come into play, which are not shown here. So your population is always dynamic. It's not only large, it is dynamic. Out of this population, I take a snapshot. That snapshot is called my training set. Snapshot is static. It doesn't change, and it's smaller in size. In this snapshot, I create a very complex model to separate the greens from the reds. Zero error in training. I take another snapshot of this, and that snapshot, the data points might lie somewhere else because they're jiggling when you're capturing them. They might lie somewhere else with respect to their central values. When I bring this model and project it onto this, it starts doing errors which it was not doing earlier. So you are in an overfit zone when your model is extremely complex and gives you very good results in your training set. But when you take that model to the test data, the model's performance drops. That happens because you absorbed the patterns in all the distribution patterns, the random noise in this data set you absorbed into your model. But that model, when you put into this, the noise is different. Noise is the jiggle, how far away the data points are from the central values. It's different, so the model performs poorly. There's no exact point. This is the only way, I told you, right? The point where they deviate. That is likely to be probably the best fit. Probably. Use a mic. Where is the mic? Please pass it on to me. Please pass it. We'll discuss this point, and then I'll take one more slide. Hopefully the concept will fall in place, then we'll move on. Yeah, go ahead, shoot.
Point.
Best fit line.
Yeah. But you continue to use the model in production, your noise will continue to increase after a period, right? Which means your best fit line will keep changing.
Okay. What he's saying is, let me correct me if wrong. It's actually a very important point. A model is not for life. Every model will need to be recalibrated. How frequently you recalibrate the models to get the same accuracy level depends on your domain. Now, I took the example of time taken to travel from A to B is a function of I built a model. But that model which I built 3 months ago will not work in today's environment because the reality has changed. The reality in the outside world has changed. There are so much of construction activities going on, so the time it's going to take from traveling from airport to this place is going to change. So all models in the real world, they will drop in accuracy over time because the population keeps changing. What you're saying is right. Yeah, there is. You can actually track the drop in performance of your models over time, and below a certain threshold, if you people have come from the quality world, we use something called control charts. The control charts have upper control limit and lower control limit. So the moment I see some trends within the control chart or going above them, then something is going wrong. Your model is a process. A process behavior has to be mapped. No. I am not aware of any formula where you can fix up the frequency. No, it's not there. To my knowledge, it's not there. You'll have to keep a track on this. There has to be a feedback loop. Feedback loop may be automatic or through a manual process, but it has to be. Yeah, a lot of people do that. They automatically capture your data from you. They do that. There has to be a feedback loop, otherwise we can't do it. Yeah. Yes. You have. Right? All right. One last PPT, then we'll break for tea. And that is about this iris data set. I hope really it will bring in the problem clearly to you. This is my iris data set. All of you know iris data set. It is about the plants. In that, there are 3 types of plants. I don't know the names, but blue, red, and yellow. This is the distribution of the plants on one particular attribute. The sepal width, one particular attribute. This is how the data is distributed for the 3 different classes. This is the entire data set. Out of this data set, I take a random sample. I break that sample into train set, test set, 70, 30, 80, 20, whatever. Look at the difference in distributions. Look at the yellow. The moment you take a sample, you change the distributions. Even if you use random functions. The moment you change the distributions, you change the central values, the mean and the medians. The moment you change the mean and the medians, the model, the linear model which you're building, which goes through the mean and the median with central values, the model will change. If you have built a model on this, the model would have been different than what you found on this. That is why when you take this model and put into production, the model will perform more errors. Now look at this carefully. So when I took a sample from this, the distribution changed, and look at the difference in distribution of the train set and test set. When the distribution is so different between the train set and test set itself, how do you expect a model which is performing well here to perform well here? Look at the second line. Another random function on this and second set of samples. Look at the difference in distributions. The data is same, but I took 2 samples using random functions. The distributions changed. So whenever you do sampling, you're introducing bias errors. You can't escape it. So when you break that data into training set, test set, you introduce more bias errors. That is why a model which performs well in training is unlikely to perform equally well in testing or in production. And decision tree, it is non-parametric. We have no parameters to control and find the best fit. So I'll create a complete complex model in your training set. So in training set, decision tree will give 0 error. That tree, when I take it to this, the distribution is completely different. So the tree will perform poorly. This is a particular characteristic of this particular algorithm, where it can easily become overfit. So we will use regularization techniques to prevent it from becoming overfit. The question that he asked was, if I got him right, the question that he asked was, should the entropy at this plus this be less than this? That's what he asked. That's what he asked. Yes, the answer is the entropy at the child level should be less than the entropy at the parent level. I'm not saying entropy of this should be less than this should be less than this. I'm not saying that. I'm saying the total entropy at this level should be less than entropy at the parent level. Child level, parent level. Okay? All right, let's move on. Now, this might look like slightly dangerous stuff, but believe me, it's very simple. Right? Don't worry about this. You understand the concept. It's important. Formulas are all there in the libraries. We just need to download the library and use it. But it doesn't hurt to see the formula and the concept behind it. So don't worry about the formula. Let me explain this to you. There is a history behind this. The history is, there was a person called Shannon, Claude Shannon. Heard of his name? Claude Shannon? Claude Shannon? Who says yeah? Anybody who's heard his name? Exactly, Molly. Yeah, you're right. Hey guys, he is one of those guys because of whom we are earning our bread and butter today. He was the father of comp science, Claude Shannon, information theorist. And he did a very fantastic job in this area. So I think it'll be good if you just go and explore on Google who this guy is, what did he do. What he said is, Claude Shannon said is, he made a graph where this represents the relationship between probability and entropy. Entropy shown by the symbol H. He had a physicist friend who was expert in thermodynamics, and we come across entropy in thermodynamics, and this guy unfortunately asked him for a name for this concept, and that guy said entropy. Otherwise, there was no reason for it to be called entropy. Okay, he wanted it to make it look something great. Okay, it is great, but it's called entropy. What happens is when you're in a situation where multiple outcomes are equally probable. We had blue and red. When you put your hand into that bag and pull it out, the probability of getting red was 2 by 4, 1 by 2. Probability of getting blue was 2 by 4, 1 by 2. You are in a situation of maximum uncertainty. You didn't know what's going to happen. Uncertainty is measured on a scale of 0 to 1. So when you are in a situation where you have to take a decision and it can lead you to multiple states with same probability, you're in a state of maximum uncertainty. So probability is 0.5, maximum uncertainty. Are you all with me? When we took that bag where two of the pen caps were blue and the two of them were red, the probability of getting red and blue was 0.5. At this situation, you had maximum uncertainty, 1.0. I replace all the red with blues. 0 uncertainty. So when you know the probability of something happening is 1, the probability of this, suppose this is probability of picking up blue from the bag. When you know the probability of something happening is 1, there is 0 uncertainty. So you are at this point. Are you all okay? With me? Lady at the back, what's your name? Yeah, you. Tamil Selvi. Yeah, got it right?
The probability is, we are not caring about the probability. We are coming to a conclusion that this is a defaulter and this is not a defaulter. But all the learning models is about predicting something. So in that case, how do we say this is a model where we can say the probability? It is like confirming that this belongs to this group.
No.
So
yeah. See, all these good question. Did you get what she's asking? Though I was expecting something else. What she's asking is the decision tree at the leaf level, if it's going to classify something as default or non-defaulter, right? And you're talking about probabilities. All these classification algorithms, whether you use decision tree or logistic or naive Bayes, anything, all of them have a function. That function is called proba. Predict dot proba. Proba stands for probability. You don't want classes, you want probabilities, it will give you probabilities. So decision tree can give you probability values. Right? Does that answer your question? Okay. All right, shall we move on? Yes.
I just get a feeling that it is looking like the probability prediction of a logistic regression.
Boss, all these are same concepts coming in different bottles.
Okay.
I'm glad that you noticed that. All these algorithms do the same thing in your feature space, in your mathematical space, but they do it in different ways. Right? So it's a very interesting thing when we, unfortunately, you people have not covered. Once you cover all these algorithms down the line, then hopefully one day we'll meet where I'll show you how these different algorithms do the same thing, but in different ways. So you got it right. Shall we move on? Any questions? No? All right. You understood these 2 points? What Claude Shannon found out is in mathematics there is a function. That function is called log to the base 2 of pi. This function takes a beautiful shape like this. Log to the base 2 of pi, when pi is 1, log to the base 2 of pi is 0. Actually, it has a negative term. I'll talk about it later. So when log to the base 2, you can do it on Google if you wish. This is equal to 0. Log to the base 2 of 0.5 is 1. So he found out one function in mathematics. He knew it. It gives you this relationship between the probability and the entropy. However, there's one small problem. The problem is log to the base 2 of anything less than 0.5. It tends to go towards infinity. It goes towards infinity. We want it to come down towards 0. We want it to come down to 0. Yeah, it is a minus. I removed the minus term right now, but it is a minus. So I want this curve to come down. To make it come down, I multiply it with by pi. So probability of getting blue, when it is 1, this becomes 1, this is 0, 0 and 1 is 0, so on and so forth. When probability of getting blue is very small, this small term will pull this whole thing down. This term is going towards infinity here, but this pi will pull it down towards 0. Hence, this equation which you see here, entropy is a function of pi log to the base 2 of pi. This expression reflects the relationship between entropy and probability. Don't worry about the formula at all. Just keep in mind how the probability of something happening or not happening is related to entropy. That is uncertainty. That's all you need to know. Okay, formula and all is not required, but this is what happens under the hood.